pretty much people having an emergency fund and how much you would have saved just in case something happens. So number 5, no, 5C, not 6C. Yeah, sorry. Okay, so looking at number 5, talking about the summer vacation and families that own computers. Kind of random, but hey, you can ask any questions you want. So C says find the probability a family is taking a summer vacation this year or they own a computer out of the ones that we're surveying. So how many families took a summer vacation? Jillian?
77.
Yeah, so the summer vacation is at the top. That's the column that says yes going down. So there were 77 families that took a summer vacation. And this is out of the total of 104. And then we want to know how many families own a computer. So, Jillian, how many families own a computer?
45.
45. Out of, again, the total of 104. So we're looking at all the families that go on a summer vacation, all of the families that own a computer. What else do you have to do with this problem? Julia?
Subtract 37 over 104.
And why do you have to subtract 37?
That's overlapping information.
Right, that's the part that is both. So we have the probability of one, we've got the probability of the other, but these are events that are overlapping events. They're not mutually exclusive or disjoint. So they overlap because there is a time where they both are being counted in owning a computer and also going on a vacation. So we need to make sure that you're subtracting that amount. So Julia, when you add the 77, 45, subtract 37, you get
85 over 104.
85 over 104. And that does not reduce. So that's the part where they both occur. So the probability of A plus the probability of B minus the probability of them both happening. And that's A and B. And that's when the events overlap. So when events overlap, it means that they're sharing something. The part they're sharing is where they're doing both. So those are called overlapping events versus mutually exclusive events. Mutually exclusive are separate, overlapping, share. They're different from dependent and independent. Other questions that you'd like to go over from the homework? Must be a long week. You all look pretty tired. So today we are going to do the last set of probability problems, the last type of probability, and we call it the multiplication rule, but it deals with finding probability of independent and dependent events. So we will be kind of using some conditions, but the condition will be embedded in the probability that we look at, how one event might change the effect or the occurrence of a second event. On Monday, for those of you that will be here, we'll be working on a probability worksheet in class. Tuesday, we will review the combinations, permutations, counting principle, and probability, as well as ops. And then on Wednesday next week, you'll have the probability test. And I will send out the solutions through Remind for the 2 probability worksheets Monday morning. Also send those out. So in your packet, this should be the last section. It is 10.5 again, but it's like part 2 because we also did 10.5 yesterday. So we're going to start off by looking at the independent event case. And then we'll also talk about dependent events. So independent events is kind of what we finished with yesterday. Does anybody remember what independent events would be? So it was the first 4 questions on your homework kind of had you determine if it was independent or dependent. And that's what we ended with. Julian?
It's not like multiple events, but like what you do for the first one doesn't affect the outcomes of the other.
Exactly. So it is multiple events. It could be 2 or more. And he said the outcome of the first event doesn't affect the outcome of the next. So pretty much the first event doesn't affect the second event doesn't affect the third event. Right, 4 things going on, that third event doesn't affect the fourth. It doesn't change the occurrence of whatever's happening next. So it is called the multiplication rule because we're going to be multiplying the probabilities together. So we would take the probability of A times the probability of B. Because if you want 2 events occurring, the probability of that happening is less likely than 1 event or another event occurring. So when you multiply, you get a smaller probability. It says more generally, the probability that n events occur is the multiples of the n probabilities of the indicated events. So it doesn't matter how many events we have. If I have 15 events, I'm going to multiply the occurrence of each event together. So there is one problem underneath here. It asks us to find the probability of 3 independent events. So the first event isn't going to affect the other event or change the occurrence. Every morning, one student in a class of 24 is randomly chosen to take attendance. Part A says, why is this scenario an instance where we could consider the formula for independent events? So one student in a class of 24, which today there are 25 of us, is chosen randomly to take attendance. Why would that be considered an independent event? Julian?
The student can still take the next day.
Yeah, so I could choose the same student every day. It doesn't eliminate that student. Or I could pick a whole bunch of different students and just go in order and make sure everybody gets a shot at it, which is what they do in elementary school. 2nd grade, having a chore or a job is a big deal. So it doesn't matter if the teacher picks the same person every day or they choose a different person. So if I wanted to be fair, then I would take that one person and eliminate them. But it says nothing about that. So it does not say it must be a different person every day. Just one student is chosen at random to take attendance. Again, big deal in elementary school. And then you get to take the attendance folder down to the office. You guys remember doing that? Having jobs in elementary school, being the line leader? It's fun stuff. That's why I don't teach elementary school. I can just do my own job. You guys don't need to help. But I would appreciate it if you'd offer every once in a while. So the letter B says, what's the probability that the same student would be chosen 3 days in a row? So I would find the probability that I would choose the same student 3 days in a row. Tatum, I'm going to pick on you because you're in front. And the middle. So what's the probability of me choosing Tatum on the first day, and then Tatum on the second day, day 2, and finally Tatum on the 3rd day? See, you're lucky to sit center front row. That's really what we're trying to figure out. So each day is its own probability. So day 1, day 2, day 3, choosing the same person. So we have a class of 24 students. I'm going to find the probability of choosing the same person or Tatum every single day. So the probability of me choosing Tatum on day 1 would be 1 out of 24. Because she's one student out of the 24. What's the probability of me choosing Tatum on the second day? Julia?
1 out of 48.
1 out of? It's still 24 because there's still 24 students in the class on that day. So the number doesn't change because it's just now it's the second day. I still have 24 students to choose from. So then on the third day, I still have 1 student out of the 24 to choose from. So my class size isn't growing. That bottom is always the total of what I currently have for each day to choose from. So if you multiply 24 times 24 times 24, you'll see that the probability is pretty small of the same student being selected on 3 days in a row. What is 24 times 24 times 24? Julian?
13,824.
13,824? Questions. So that is an independent event. The same person is chosen, that one person, 3 days in a row. And I still have 24 students when I come in the next day and I choose that same person again. So the question at the bottom says we want to use the complement to find the probability. Before we look at the question, does anybody remember what the complement means? So we did this, I think, on Tuesday. We talked about the complement. There was a little notation we used. Odette, do you remember?
When you find the probability of like what the question isn't asking.
Right. She said what the question isn't asking are kind of like the opposite of it. So we're going to find the probability of the complement, the opposite, or not the event happening. And to do that, we usually take 1 minus the probability of the event. So we're going to see if we can try and use this complement to help us find probability. Because sometimes the complement's like the shortcut way around getting the probability. So while you're riding to school, this should really say your smart device plays 4 different songs from an album that has 16 songs in it. So whatever you use to listen to music, you all carry around your devices. You probably have millions of songs stored on there, way more than I probably do. What is the probability that you will hear your favorite song on the album at least once during the week? And it has 5 days there. So let's kind of talk about this. Looking at, we have 4 different songs on your ride to school. There are 16 songs to choose from. Let's just start with that piece of information. So during your ride to school, you get to listen to 4 songs. That's how short your trip is. So maybe like a 10 to 12 minute trip, depending on how long the songs are, maybe 16, somewhere in that vicinity. And you have 16 songs to choose from. What type of problem is this? So I have a total of 16 songs. We're listening to 4 of them. So we have to first decide, like, what do you do with those 2 numbers? We want to figure out the ways or the probability that we could listen to our favorite song. Julian?
How do you find the combination?
Yeah, this is a combination. So we first have to figure out how many different ways I can listen to those 4 out of 16 songs. And that's going to be our total. So the total number of ways is a combination because there are 16 songs. We're going to listen to 4 of them. So I first need to figure out what's that bottom number for the probability. Because probability is what you're looking for on the top versus the total number of options on the bottom. It doesn't give us a total number of options. We have to calculate it. So with your calculator, see if you can take 16 combination 4. Oh, you have your calculator. Does it work? Wow. So this just gets us the total. Because anytime we have probability, we've got to know what we're working with. What's that total? So Connor, what's the total if we have 16 songs and we want to listen to 4 of them?
We could have 1,820 combinations.
1,820 different combinations. So that's our total. That's going to go on the bottom. Now we need to figure out what we're trying to find. So we have the total number of ways that I can listen to 4 songs on my ride to school. That's a lot of ways. It says, what's the probability that you will hear your favorite song on the album at least once during the week? What does at least once mean? Julia, what do you think at least once means?
Like one or more times.
1 or more times. So maybe I hear it 1 time, 2 times, 3 times, 4 times. I could possibly hear it 1,820 times if I had the amount of time. So the reason we're using complements is because at least once means a whole bunch of times. And finding the probability of essentially a value that's pretty large would take a lot of work. So we're going to use the complement, and instead of saying find the probability of at least once, we're going to find the probability of not hearing the song. Because I'd either hear it at least once, or twice, or 3, or 4, or 5 times, or I don't hear the song at all. And it's a lot easier to figure out the probability of me not listening to that song than it would be of me listening to that song multiple times. So we're going to try and find that probability. That means we're going to take 1 minus our probability. And on the bottom of that probability is 1,820, because that's the number we already calculated. So now we have to do the top. And the top would be the probability that we don't hear our favorite song. So there are 16 songs to choose from. If one of them isn't my favorite song, now I have 15 songs remaining. I'm still wanting to listen to 4, but I'm not listening to my one favorite song, so that song is getting excluded from the list. So we have the 1,820 ways that I can listen to 4 out of 16 songs. Now I want to know, if I take my favorite song out of the options, how many ways do I have to listen to the other ones that would not be our favorite song? So don't finish calculating the probability, just do that combination part. Julian, what's that combination?
1,365.
365. Okay, so this problem is like a pretty involved problem. There's a lot to think about. There's still one more thing that we have to do. So right now we have it set up that I'm finding the probability of not hearing my favorite song, which I would take 1 minus, this is the probability of not hearing my favorite song. So if I do the opposite of it, then I can find the probability of what we're looking for. However, this says during the week, and it has 5 days there. This would just be for day 1. This is the probability of me not hearing that favorite song on the first day. But we have 5 days. So because it's 5 days, this probability, you either need to multiply it by itself 5 times for each day, like we did with Tatum, multiplying 1 over 24, 1 over 24, 1 over 24, because that was 3 days. Or, come on buddy, here it goes. What could I do with it instead of showing and multiplying it together 5 times?
Can you put like a exclamation mark?
You could put the exclamation mark, we could just raise it to the power of 5. So we can just raise it to the 5th power because I'm trying to do the same exact thing for 5 days in a row. Just like we were trying to choose the same person for 3 days in a row. So again, we're using complements because we're taking 1 minus the opposite of what we're looking for. And if you take 1 minus the opposite of that value, then you get the at least once during the week. So in your calculator, just be really careful and make sure you're putting that number in parentheses, raising it to the exponent of 5. It's probably going to give you a decimal. I don't know if does it put it in fraction form for you? It does? Odette, what did you get?
I got 181 and 1,024.
And I think as a fraction, that's like 0.75? 0.76, it is one off. As a decimal, it's about 0.76. So about 76% chance that you'd listen to your favorite song at least once during the week, which is a pretty good chance of it happening. Questions, because that's a hard problem. So the reason we're using the complement is because it's easier to find the probability of not hearing that song than it is to hear the song. So if you flip the page and you look at the top of the next page, there's two little problems here, practice problems. So we have a track meet. Each race consists of 9 competitors who are randomly assigned lanes from 1 to 9. What's the probability that a runner will draw lanes 1, 2, or 3 in the 3 races that he competes? So we want to find the probability for race 1, race 2, and then race 3. That he would be in lanes 1, 2, or 3. So Emma, how many lanes are we talking about here? 9. And we want to find the probability that he would be in lanes 1, 2, or 3. So that would be 3 different lane options. So the 3 lanes, 1, 2, or 3 out of the total. So that's for race 1. The probability for that occurring for race 2 is 3 out of 9. For race 3 is still 3 out of 9. Or you could say 3/9 to the 3rd power, because the same thing is happening repeatedly for each one of those races. So Emma, if we multiply them and reduce that, that gives you 27 over what? 729. And then that goes down to yeah, 1 over 27. So if you have the same probability for this number of days or the number of races, then it's just that probability to raise to the exponent. That's the easy way to think about it. Looking at the next one, this is going to be similar to the at least once. It doesn't have to do quite as, this one isn't as detailed though. So a manufacturer has found that 6 out of every 450 batteries produced is defective. If something's defective, what does that mean? Julian?
It has problems that make it not work.
Yeah, it's got some kind of problems. It's not going to work right. So 6 out of every 450 batteries is defective. They're not going to work right. What's the probability that at least one battery is defective the first 100 produced? So here's that at least one. So we're going to find the probability that it's not defective. So we're going to take 1 minus the probability that it's not defective. So Mackenzie Myers, how many batteries are we talking about? How many total batteries? 450. Mackenzie, if 6 out of every 450 are defective, how many of them are not defective? So 444 of them are not defective if 6 of them are. So we want to do this 100 times. So that means that value here, the probability that they're not defective, 100 times, or to the 100th power. Because I want to test this 100 different times to see what the chances are of me getting a battery that would not be defective. So then I would flip that and say, what's the probability that at least one battery is defective out of the first 100 tries? And that's why we're using that 1 minus. Kushal, what'd you get? Yeah. So 0.74. So 74% of the time, you're going to get a battery out of 100 of them that would be defective, which makes sense. I'm sure out of 100 batteries that you choose from, one of them probably isn't going to work like it's supposed to. Questions? The other type of probability we're going to look at today would be the dependent events, where the first event changes the occurrence of the next event, or changes the outcome. So the problems that we've looked at were called independent because the first thing didn't change or affect the outcome of the second. So this probability is found by taking the probability of A, the probability of the event happening first, because there's not going to be any change. And then you're multiplying that with the probability of B given A. So that means I'm finding the probability of B after the A has occurred and changed the outcome. And that's that line, that given information that we talked about yesterday. So we're still finding the probability of A like regular, but we have to think about what B is and how that change has affected B. So if you look underneath, this one says you randomly select 2 cards from a deck of cards. What's the probability that the first card is not a heart and the second card is a heart? And it says we're trying to compare how to do one versus the other. The first one, you replace the first card before selecting a second card. So when you see the word replace, that means the card was pulled out of the deck and placed right back in it. So I started with 52 cards, I took one out, but I put it back in. So we're trying to find the probability that we have not a heart, and then my second card is a heart. It's a pretty crappy looking heart. That's a little better. So thinking to a deck of cards. What's the probability that you would not get a heart? How many cards are not hearts? Odette, how many cards are not hearts? Use 39, not 49. I was going to say 49 is a little high. So 39 out of 52 cards, because 13 cards are hearts, 13 cards are diamonds, 13 cards are spades, 13 cards are clubs. 13 of each of them. So not getting a heart would be 39 out of 52. And means multiply. There is no change because you take the card out, you place it back in. Odette, what's the probability of choosing a heart the second draw? 13 out of 52. So you take the card out, you place it right back in, and I still have 52 cards because I replaced it. Maggie, what'd you get when you multiplied those together? 3 over 16. All right, so let's see how the next one differs. It says you do not replace the first card. So we're still finding the probability of not getting a heart and then getting a card that's a heart. So the first one isn't changing. It's still 39 out of 52. But now we've taken that card out and you kept the card. So what's the probability of choosing a heart on your second draw? Odette? 13 out of 51. Because now I have one less card in the deck. And that's that probability that's changing. Because I had 52, you took out one card, so I have 51. And Odette, what would that probability be reduced?
13 over 68.
Questions? So there are some practice problems on the back. Or not. Where's example 4? Is that at the bottom or the back? It's at the bottom. Okay. I lied. So at the bottom. So a teacher passes around a box with 10 red pencils, 8 pink pencils, 13 green pencils. If you and the 2 people in your group are the first to randomly select a pencil, what's the probability that all 3 of you select pink pencils? So there are 3 people. You want to find the probability that the first person, maybe you, we'll say you, select a pink pencil. You want to find the probability that the second person gets a pink pencil, and then you want to find the probability that the third person in your group gets a pink pencil. So start with the probability of just you getting a pink pencil. How many total options are there to choose from? So I have a little bucket on my desk that used to have a lot of pencils in it. It has barely any, but let's assume that I had a whole bunch of pencils in my little can. And I pass this to you because your group is first. What's the probability of you getting a pink pencil? Matt, how many total pencils are there in my little can of pencils? 31. What's the probability of you getting the pink pencil, Matt? 8 out of 31. Because there are 8 pink to choose from. So now Matt has chosen the pink pencil. Matt, what's the probability that Garrett in your group gets a pink pencil? 7 out of 30. And then Matt, what's the probability that Brock also in your group gets a pink pencil?
6 out of 39.
Nice job. So each time you're pulling a pencil out, but you're also getting that pink pencil, so that number is reducing every time. So my first option is the total, and then each option remaining, you lose a pink pencil and you lose a total from your group. So Matt, that number would be?
56 over 4,490.
Questions? So why don't we just look at why don't you do that example? I think yours says 3, mine says 4. So from example 4, what's the probability that both cards are jacks if you replace the first card and do not replace the second? So example 4, just reminding you what example, randomly select cards from a standard deck of 52 cards. What's the probability of now getting 2 jacks? So that really means I'm finding probability of getting a jack and then another jack. The first one says if you replace the card. B is if you do not replace the card. Connor, how many jacks are in a deck of cards? 4. So if you take out the card, you replace it back into the deck, what's the probability of getting a second jack?
452.
Yeah. And that reduces to?
1 over 169.
So part B is the same question. We want the probability of getting a jack and then a second jack. So the first probability isn't changing because I have 52 cards. What's the probability of getting a second jack? If I take that card out and I don't replace it, Connor.
30 over 51.
3/51. And that reduces to 221. Questions? So we'll stop there, we'll get the rest of them on Monday. Remember this worksheet, you have the solutions, that solution sheet was passed out to you on Wednesday, so you still have the solutions to this multiplication and worksheet.